Welcome to this explainer. Today we're going to take a very precise descent into the absolute fundamental architecture of reality itself. We're going to strip away the everyday illusions we hold about the physical universe, and we're going to look closely at the cold, elegant geometry that actually governs existence at its lowest level. So no hype, no mysticism here, just a highly structured journey directly into the deep engine of physics.
We're all taught from a really young age to think of mass as something material objects simply carry around, right? We intuitively picture it as an internal weight, some kind of built-in heaviness, like a permanent property that's securely placed inside matter. But what if we've been looking at it completely backward? What if we challenge that intuitive, everyday illusion right now? Let's ask a deeply profound question that's going to frame our entire journey today. What if mass is not stuff inside matter at all?
Section 1. The Standard Model Account.
Okay, let's dive into this. When modern physics asks where mass comes from, it definitively points to the Standard Model, and specifically, the Higgs field. Now, popular science often resorts to analogies here, right? Calling the Higgs field a cosmic syrup, or maybe comparing it to a crowded room that slows particles down as they try to move through space. But to truly grasp the physics, we need to intentionally avoid those childish analogies. The deep engine of reality recognizes no syrup. It operates purely on mathematics and symmetry. So let's look at the factual sequence of what actually happens. At ultra-high energies, like those in the extremely early universe or within the deepest reach of a particle collider, the electroweak sector is perfectly symmetrical. In this state, particles exist without our familiar rest mass, because the system just hasn't yet committed to the broken phase. But as the universe enters a cooling phase, a massive shift occurs. The Higgs field acquires what physicists call a non-zero vacuum expectation value. The underlying symmetry breaks. And it's through this subsequent coupling, the interaction between particles and this omnipresent field, that our familiar particles finally gain mass. This sequence, known as electroweak symmetry breaking and the Higgs mechanism, is the scientifically rigorous, universally accepted field-theoretic explanation.
Section 2. The Limits of Higgs.
And this brilliantly illustrates a crucial scientific caveat. Because we need to pivot structurally here to clarify exactly what the Higgs mechanism does, and maybe more importantly, what it doesn't explain about the physical universe. It's a flawless mathematical model for fundamental particle mass. But if you think the Higgs field is solely responsible for all the weight of the objects around you, well, there's a massive piece of the puzzle missing. When comparing the origins of mass in ordinary matter, there is a tiny sliver that represents direct Higgs coupling. That's the mass of the individual fundamental quarks and electrons. But the massive slice taking up almost the entire picture, that represents QCD binding energy. See, most of the mass of ordinary matter, the protons and neutrons making up the stars, the planets, and literally your own body, comes from the immense energy binding those quarks together. It's the result of quantum chromodynamics, where the vacuum dictates that colors simply must close. So the Higgs alone does not explain all the mass in the universe.
Section 3. Beneath the mechanism.
So we've firmly established the accepted field-theoretic explanations. We know the Higgs gives mass to fundamental particles, and we know QCD binding energy accounts for the bulk of composite matter. But now I really want to invite you to cross a threshold with me. What if we transition from these accepted physical mechanisms into a much deeper structural inquiry? This brings us to a framework known as General Emergence Mechanics, or GEM. Let me be perfectly precise here. This is not a replacement for the Higgs mechanism, a geometric question beneath it. GEM is a developing, exploratory, and highly speculative framework. It asks what the breaking of symmetry actually means geometrically. It investigates the hidden architecture of reality, asking how possibility loses its freedom, and exactly what happens when an open route is forced to lock into a constrained trajectory.
Section 4. The Geometry of Commitment. Now, what's really interesting about this slide is the dramatic contrast. To understand this geometric shift, I want you to visualize a stark, absolute black canvas. Across this deep navy, almost pitch-black coordinate grid, imagine a blinding white vector line. It twists, loops, rotates, and folds effortlessly. It moves through higher dimensional gates and completely unbranched routes. Nothing catches, nothing resists. It hasn't yet been forced to become local. This is the state of the universe before mass. It's not emptiness, it is absolute, unbridled, geometric freedom. Before the transition, we have this ultimate freedom, phase freedom, rotational freedom, unbranched access across the deeper lattice of possible structure. The route has not yet been forced to choose. But look at what happens after. The temperature falls, the boundary is hit, and absolutely everything changes. After the transition, the route locks. It triggers amber-lit warnings of collapsed freedom. The trajectory becomes local. it's heavily constrained, and most importantly, it becomes highly resistant to motion.
The fundamental architecture of reality dictates that this unbounded freedom cannot last forever. When the energetic conditions of the universe change, the vacuum utterly refuses to allow infinite possibilities to remain open. The options collapse. The phase is forced. Symmetry must commit.
So the crucial point is this: what happens when a route locks into place? Well, a committed route violently resists being moved. It's no longer flexible, it's permanently anchored into a constrained trajectory on the modal lattice. When we try to push a physical object, when we try to alter its path, we are fighting against that geometric lock. That resistance to motion is exactly what we measure in physics. Inertia is the drag of a choice already made. And this brings us to a radically different perspective on our initial question. If inertia is simply the drag of a geometrically locked route, then mass is not some magical property imbued into a particle. It's the inescapable cost of losing phase freedom. When a system undergoes electroweak symmetry breaking, it makes a choice. It locks its route. Mass is the receipt of that commitment. We started by looking at the Standard Model and the Higgs field, and we've journeyed down into the stark, rigid geometry of reality itself. We've seen how unbound vectors lock into constrained trajectories, and how that very constraint gives rise to the drag we call inertia. The implications here are profound, and they challenge absolutely everything we intuitively feel about the physical world. So, I want to leave you with this final thought, to reconsider the next time you look at the solid objects around you. Mass may not be what matter carries. Mass may be what possibility pays when it becomes real.